This video presents the UK demonstration case developed for the Accord project. Funded by Horizon 2020 and UK Research and Innovation, the project explores automated compliance checking in construction. The UK case represents the result of a 3-year collaboration between Birmingham City University and Ether Engineering. The demonstration focuses on automating the verification of structural integrity in modular steel housing. By combining semantic web technologies, open-source structural analysis, and BIM data, the tool supports regulatory checks against Eurocodes. Compliance is reported through a web-based user interface. This case centers on a modular housing system developed by Hadley Group. Our focus is on ensuring structural compliance during the design and manufacturing stages using Eurocodes 0, 1, and 3. The core aim of this demonstration is to automate structural compliance checks using enriched BIM inputs and finite element analysis. This helps reduce manual interpretation and supports modular construction workflows with timely, standards-based feedback. The compliance process targets 2 key areas: structural member checks under ultimate limit state conditions, and parameter checks verifying correct application of Eurocode values. This is achieved using a multi-platform approach, linking IFC-based models, simulation engines, and semantic rule systems. This approach adopted is explained in the academic paper, Semantic Web-Based Automated Compliance Checking with Integration of Finite Element Analysis, published in Advanced Engineering Informatics. The demonstration begins with a structural BIM model. The model is evaluated through a web interface that allows users to register, upload their IFC structural model, and initiate analysis. Behind the interface, enriched BIM data is processed to conduct structural member checks automatically. To use the system, users begin by registering their email address. This creates a secure workspace to manage and store their projects. Once registered, the user creates a project. Each project corresponds to one structural model to be analyzed. The next step is to upload the BIM model in IFC format. This model serves as the basis for structural validation. After the upload, the system automatically parses the model. It identifies key features, such as curved elements, joints, and loading actions, then classifies them according to spatial structure and member type. The IFC data is then passed to CodeAster, an open-source finite element analysis engine, to simulate structural behavior. Users can visualize the model using a structural member diagram view, which displays how the model is discretized for simulation. The analysis workflow is structured in 3 simple steps. First, define the mesh length. Second, load the simulation results. And third, generate compliance check results. In this example, the mesh length is set to 1,000 millimeters, which is the size of the finite elements used to discretize the structural member of the analysis. The mesh analysis result is now loaded to the tool to generate the validation. Next, the system generates a validation report. This shows the type of checks performed, such as shear resistance check, and the utilization ratio for each structural member. Green ticks show members that pass, red crosses identify failures. Users can switch to alternative visualizations to examine the results in detail, aiding interpretation and verification. A workshop held in March 2025 brought together architects, engineers, manufacturers, and digital specialists to evaluate the tool. Participants recognized the value of automation in reducing ambiguity and aligning with established standards. They confirmed the tool's technical feasibility, currently at technology readiness level 5 to 6, and highlighted the importance of transparency and explainability of logic. Scalability was seen as achievable, especially in modular workflows, if the tool integrates via APIs and gains recognition from public authorities or warranty providers. The tool's modular rule engine was praised for its extensibility, with potential to support additional domains such as fire and accessibility. This diagram shows how the UK demo fits within the Accord cloud architecture. The tool supports rule formalization and connects to a potential data dictionary for structural checks. We encoded several Eurocode-based rules and demonstrated the use of information delivery specifications for model validation. The system outputs both model validation data and FEA results, which could serve as the basis for cloud-based permitting or self-checking tools for modular designs. Together, these functions contribute toward a scalable compliance-checking microservice that aligns with Accord's vision. Thank you for watching. To explore the project further, scan the QR codes shown here or visit the Accord project website.